running time, because I want C to be independent of K. Okay, so that is our goal. Now, what else can we do? We can kernelize it and then do this brute force. Okay, that actually gives you an FPT algorithm. In fact, we even discussed that is one motivation for actually kernelization. So, once I kernelize it, now I look at this equivalent instance and ask the question, and that would be, now n has gone away. So, it is like 2k choose k, some k square. So, 2k after kernelization, right. And this is like 4 power k times k square. There is also another way to see that I suppose I look at all possible subsets of the vertex set without even looking at the size bound. That also is about 4 power k, 2 power 2k, right. So, that gives me one FPT algorithm for this problem, which is kernelize it and then do brute force. Okay. Now, we want to think of better FPT algorithm. What does better mean? Better in terms of the f of k, also in terms of the polynomial, okay. But the primary thing is to just reduce the f of k even better, right. Currently, it stands at 4 power k in what I have seen. Can you do better than that? Okay. So, yesterday you would have seen a flavor of different kinds of branching for this bounded search trees for vertex cover. So, the idea is, instead of trying all possible subsets, you somehow figure out certain subsets are anyway meaningless, and then try and prune them, right. So, if for example, if you have an edge in the graph, then any subset that does not even touch this edge, do not bother exploring, because every vertex cover must have at least one endpoint of this edge. So, we want to sort of formalize that idea and systematize it, that I am not going to branch every possible subsets, but some carefully chosen subsets. So, this suggests that this idea of pick an edge and branch, right, or yeah. So, branching, I mean, we saw this again yesterday, right. Vertex cover G k, pick edge u v from the graph. So, the observation is that u or v must be in any vertex cover. So, I will try u. So, I am guessing, in some sense I am guessing a choice, and so we will look at all solutions that contain u, all solutions that contain v, and explore them. So, pick edge u v, check. Now, remember, the k is something I want to really make use of. I am not looking for a minimum vertex cover, I am looking for a k size vertex cover. If it is something more than k, I am not interested in. So, I will say check if Vc of G minus u k minus 1. I pick u into my solution, and in the remaining graph, which means I delete u, and check whether there is a vertex cover of size k minus 1. If that happens, then I know the answer is yes. I will pick my k minus 1 size plus attach this. Okay. So, if or this is, now this is a recursive call, return no, else, sorry, return yes, and not just return yes and no, you also can return the actual vertex cover size. Okay. So, now where does this process end? K might become 0, or there is no edge in the graph, right. So, we will add this end condition, if k is 0 and you have, okay, yeah, k is 0 and there exists an edge, you return no, and if k is 0, there is no edge, then return yes. Okay, can you hear me? Yes, can you hear? I am going to continue, and if there is no h, and k is greater than or equal to 0, then you say yes. Okay, so this is the entire algorithm, which is a recursive algorithm. Now, how do we analyze this algorithm? Okay, and so I believe you would have seen even more sophisticated branching, but we want to just step back, talk about how do I analyze such algorithm, right? It is a recursive algorithm, so we will use recurrence relations to analyze this algorithm. And so, one way to visualize this is that you have a search tree where you have a G, and this would be G minus U, K minus 1, G minus V, K minus 1, and then you are going to pick some other edge here and it will branch, and finally you stop at some simple cases of the leaves. Okay, the leaves of this search tree. The simple cases are that maybe k has become 0, and or there are no edges. One of this happens, then you have a way of handling the giving the answer right away. Right? So, one way to analyze the running time of this algorithm is to see how the number of nodes in this tree is. This is a search. So, this is what is called a search tree, and it is bounded because somehow the height, the branching factor, at least in this example, is 2, and the height is bounded by k because at every step k drops. So, here is a simple observation: the number of nodes in the tree is at most the number of leaves in the tree. Okay, why is this? So, what is the geometric series? I see. From there, I do not see still how I get that.
The number of internal nodes will be 1 plus 2 plus 4 plus up to 2 to the power k minus 1,
okay.
which will be 2 to the power k.
Okay.
And the number of leaves.
So you can hear me now? Okay. So I am just revising vertex cover branching algorithm, which you already have seen yesterday, last week, but I want to get into the details of how you analyze not just this algorithm, in general similar branching algorithms, right. So, number of nodes is less than or equal to number of leaves, because as you say there will be one node here, two nodes here, 2 square at the next level. Some, if the k is the number of height of this tree, then it will be k minus 2 and then 2 power k minus 1. So, this is the number of leaves, which should be at most 2 times, sorry, the number of nodes is at most, or it is exactly equal to or more or less this. This is exactly what I said. It is 1 less, and so the total. Okay. Now, what I want to claim is I want to lift it a little bit and do more generally how these branching algorithms work, and I want to argue that even here, even such general cases, this is true. What is the general case I want to talk about? Before that, so my point is The way we will analyze these algorithms, we will bound the number of leaves in the search tree. Once I bound the number of leaves, you can double it to get the total number of nodes in the tree. Okay. So, the way we will analyze is running time of these branching algorithms, right. The algorithm branching algorithms looks like this. We will see how many nodes are there in the search tree totally and multiply by the amount of time I spend in each node. That will be the total time. The amount of time I spend in each node here and typically would be some polynomial time, because what am I doing? I am finding an edge and then I am deleting a vertex. That is all I am doing, right. So, that is something which you can find an edge, delete it, check, compare with something about k, that is all, right. These are just not just polynomial, fairly small polynomial time work that happens at every node. So, if I know the number of nodes in this tree, search tree, multiply by some polynomial, I get the total running time. This observation tells me that I do not even need to bound the number of nodes, bound the number of leaves in the tree, multiply by the polynomial, multiply by 2 and some polynomial, you get the total running time. Okay. So, in this case it will be two-way branch. So, what sort of recurrence relation you will get? T of k from here is at most. So, now let us count the number of leaves, write a recurrence relation for the number of leaves, right. I start with note that it is actually a 2-parameter recurrence. There is input size and k, but k is what is really playing the role. So, I am going to just use only k is less than or equal to 2 times k minus 1, because in each branch k drops by 1. This is the number of leaves, okay, not the number of nodes, because what is the number of leaves? Well, how many leaves are there on the left subtree, how many leaves are on the right subtree, add them all, that is the number of leaves. So, this has easily solvable recurrence, which solves to about 2 to the k. So, my overall running time would be something like 2 to the k times n to the some mn or something like that, very small polynomial, which is of this kind of a running time. F of k times n to the c, where c is independent of k, compared to this kind of a running time, where k was in the exponent, whereas there k is not, k has to be in the exponent. Why? I mean, I can't just get polynomial in n and k, because it is an NP-hard problem, but you have to live with exponent. What this is saying is, okay, do not sit on top of n, but sit on top of some constant. So, this is a prototypical branching algorithm. Typically, what happens? So, you have your input I and the parameter k. In polynomial time, we will break it up into some simpler instances, where in each one of them k would drop. Okay, not k, some function of k. So, I am going to say some function of k, which it will drop at every step. So, this for now let us say k drops. So, here I would say maybe some I1 k minus d1, I2 k minus d2, okay. So, what is the step, which simply says take your instance, do some polynomial time computation and find some L different guesses, each one correspond to one of the branches of the search tree, and so you make some guess here. So, it is not, yeah, and you get a reduced instance I1 and new parameter k minus some d1, and similarly here you have a new parameter k minus d2 and so on. So, and the algorithm will dictate that if you solve any one of this, or if you find a feasible solution, whatever, if any of this is an S instance, then you got a S instance for the original problem. This is the way typically a branching algorithm will work. Okay. So, how do I analyze this? Well, again I count the number of nodes in this search tree, and multiply that by the time I spend on each of the search trees. And again I claim that number of nodes in the tree is at most number of, I mean, what sort of property do I want to guarantee this? Okay, this is true for a complete binary tree, that's what it was, but I am saying that no, let's relax. What sort of property do I want for to satisfy this? You have a tree, I want the number of nodes to be bounded by the number of leaves, number of internal nodes. Or give me an example where this is not true. Path, right? You have a path, number of leaves is 1 on 2, internal nodes is huge, right? You can have any number of this. Okay, so what extra thing which was useful here, which you degree of internal vertices, what do I want? Complete ternary trees is one example, yes, but even more generally. Degree of internal vertices is the crucial thing, yes. So what do I want there?
Because in path it is internal node is
2, right.
So if it is greater than or equal to 3.
If it is greater than or equal to 3. So in particular, this is a search tree, right? Something very special. So at the root, I don't care. Degree can be 2, right? But at every, these are all branch point, right? At every point, when I branch, I make sure that I have at least 2 branches, right? It seems like a natural thing which will happen in a search tree, because you are making a guess, right? Either this guess, I mean, if it's a deterministic guess, you might as well compress that and put it here, right? If in polynomial, you're just spending polynomial time, simplifying, compress them all into one such node, and then here you are branching. So branching factor here is at least 2. Then that property is still true. Can you tell me why? Why? Because
This is ordered.
really? No. So let's, I mean, root is sort of an exception where your degree is 2. But let me just argue number of vertices with degree greater than or equal to 3 is less than or equal to number of leaves, probably even -1. This is generally in a tree. Okay, just work it out. It's just some simple calculations, but I'll just give you an online proof. Okay, what is the average degree in a tree? Average degree.
No, 2.
What is the total number of degree? Total degree?
Total degree is 2 times n max.
2 times n minus 1. So what's the average degree? Roughly by n, roughly about 2. So average degree in a tree is 2, right? But vertices with degree greater than or equal to 3 are giving me degree more than the average. They have to be offset by somebody whose degree is less than the average, and they are the leaves. Okay, you can translate it, do some calculations, and you'll get. This could be an interesting problem for your sessions. Okay. So what have I deduced? It's enough, even in this complicated branching algorithm, to count the number of leaves, because once you count the number of leaves, you also have a bound on the number of internal nodes, and then so number of leaves and the time you spend on each node, which will typically be polynomial. So, number of leaves play a role, and for the number of leaves, what sort of a recurrence will relation equation will I get if this is the kind of a branching algorithm? What recurrence would I get? So, if I do this branching and it continues like this, then what is the recurrence relation for the number of leaves? Right? T of k, I've started. Okay.
less than or equal to sigma I.
Yeah, summation I. Right. Now, how do I solve this kind of relation? It's not as, so if all the di's are same, let's do that first. That's an easy case. That's like this, right? All are 1. If all the di's are same, let's say di equal to d for all I, then what it is? What is it? Hmm?
L to z. L to z by d.
Hmm. You see this? What is the branching factor? So, this is like L, right? And what is the depth of the tree? Each time k drops by by d, k by d. So, it will be L power k by d, right? So, this running time would be so if all the branching bounded search trees solving this recurrentization is a very important part of exact exponential time algorithm. So, you want to talk about satisfiability algorithms even without the parameters in place. Okay. Take any NP-hard problem you want to solve exactly, no approximation, you want to do brute force and you want to do some careful choice of branching, you will get to something like this and you will have some sort of a recurrence and you need to solve them, right. 3 SAT, 2 SAT, hitting set, set cover, various kinds of problems you can design branching algorithms. Typically you will have this kind of a step. So, if DIs are not the same, so did you see an example last time where the DIs are not the same? For what? 1 3 for what? Vertex cover. 1 3 because what was that? So, for example, for vertex cover GK, what is the 1 3 branch?
So you look at vertices with degree at least 3.
Okay. So, let V have degree at least 3. So, in one branch you pick V. So, if Vc of G k minus 1, so you pick V into the solution, delete it and look for a vertex cover of size k minus 1. If you do not pick V, then what? I am forced to pick all its neighbors into the solution because that they are the ones who cover all the edges incident on V. So, it will be, sorry, not G k minus 1, G minus V k minus 1 or vertex cover of G minus n of V k minus size of n of V. So, if I pick V, look for a vertex cover of size k minus 1 or I pick all its neighbors and look for a vertex cover of k minus whatever I have picked. In any one of them I succeed, I know there is a vertex cover of size at most k, otherwise I return no. Well, what is the tail condition here? Every vertex has degree at most 2. How does the graph look like? Its paths are cycles and you can easily solve in polynomial time, right. So, if max degree is less than or equal to, so to solve in polytope. So now how do I solve this? What is kind of recurrence I get? T of k. In one branch it's T of k minus 1. In the other branch, since n of v has at least 3 vertices, it drops by at least 3. So since I have less than or equal to, the recurrence would be something like this. So how do I solve this kind of a recurrence relation? One, I mean, how do you solve recurrence relation? Generating functions. If you can guess the solution, how will you solve it?
Guess and substitute.
Induction. Right? So induction, let's try. Let's try the induction step. I'll tell me what sort of condition I need. Okay, so suppose some c times d power k. I don't want to use d, I will use. So, suppose it's c times f power k, where, or f times c power k, where f and c are some numbers I don't know. I'm guessing. I'm going to plug it in and verify, right? So there will be a tail condition which will dictate what f should be. Okay. So at the induction step, suppose I have that statement true up to k minus 1, then it is true for this and it is true for this. So what do I want? T of k by the recurrence relation, it is this. By induction, this is by induction, f times c of k minus 1 plus f times c of k minus 3, which is equal to f times c of k minus 1. Okay. And what do I want this to be? If the induction has to go through, I want this to be less than or equal to f times c of k. Right. So f is dictated by the tail condition I said. Let's c is dictated by this. So we want c of the c that satisfies this, right? C of k is greater than or equal to c of k minus 1 plus c of k minus 3 is what I want. So let's take off c of k minus 3 out. So I want c cubed to be greater than or equal to c square plus 1. Find the c, the smallest c that satisfies this, then you are plug it in that and that induction will go through. So that's a cubic equation. You have to solve it. In fact, the smallest c will actually have the equality there. Solve it. Solve it using whatever methods you know. What methods do you know? Mathematica, Maple. We do that most of the time actually. So this find c that is a solution to x cubed minus x square minus 1 equal to 0. So what you will have is, in general, you will have a polynomial, something like this with L terms, right, when in general. You have to solve that maybe Lth degree polynomial or something. And the mathematical theory of such polynomials tells you that there is actually a unique polynomial, unique solution which is positive. Okay. So, that positive root of this is a solution to the recurrence relation here. So, in particular, you might have seen an intermediate solution to this, right. So, do you know what that, so that this is what 1.4, 1.46 power k or something like that. So, C equal to, do I have it here? 1 point. So, we know, so one can solve vertex cover in order 1.4656 power k times k square plus some m root n. When we can do all of this after kernelization, that is a polynomial time, and so the number of vertices is only about k square. So, in particular you would have seen an intermediate branching step if delta less than or equal to 1, solve in polynomial time. Otherwise, pick a vertex whose degree is greater than or equal to 2, and then this would be like this, and this is a Fibonacci recurrence. So, you plug it in here, k minus 1 and k minus 2. So, the thing what you want is, so this would be like c square is greater than or equal to c plus 1. So, you solve the equation x square minus x minus 1 equal to 0. The solution is exactly the solutions, 1 plus square root of 5 by 2, that 1.618. Now, you get into the hang of, if you want a good branching algorithm, it tells you what sort of branching factor. So, if I want to improve this algorithm, it tells you, okay, now let us try 1.4, okay, or maybe, so what happens if it is instead of 1.2, I do 1.3.3, okay, I might have that kind of a branching algorithm as well. You will get a recurrence relation, you will get some sort of an equation, you have to find solutions, and you get the base of the recurrence tells you what is the f of k bound there. Okay. So, just like your master theorem in the classical thing, which tells you, whether the algorithm running time is n log n or n square or n cubed kind of a thing. It's just like you have it in your fingertips. You can have, some of our senior PhD students will tell you, oh, 1.3, it's 1.466, that kind of there is a table in the book which tells you for various 1.4, 1.5, 1.6 what kind of a branching factor. Okay. So, now if you want to improve it, you know what kind of fiddling around you want to do, but there is no set formula. It's, if you have multiple branching things, then life is not that easy all the time. You have to work it out, check. Okay. So, this is impressive that we started off with an algorithm whose running time is like n choose k for vertex cover, but now we can actually do something like 1.4 or 1.5 power k times k square plus m root n, and the people have written various papers on it. There are tens of papers. The current best stands at 1.27 k plus k n, or 27 something something. Very complicated set of, the case analysis will go to 3 pages of. Okay. If you have a vertex whose degree is greater than 4 and it has 3 of these neighbors of this type and 1 neighbor of this type, do this, otherwise do this, and so on and so forth. Okay. There is always a trade-off about between the number of cases and the number of digits in which you get an improvement in the running time. But still, what would be nice is to come up with some general machinery which just, with a few cases can improve the runtime. Okay, so let's see some more examples. So last time I mentioned about this feedback vertex set. Okay, in the undirected case. Right. So we have a G, K, and the question is, are there K vertices that cover all cycles? So if I want to apply the kind of branching algorithm I did for vertex cover, life becomes harder. I mean, there we said, oh, if I don't pick a vertex, I have to pick all its neighbors, and that gave me a big branching rule, right? Or you say, okay, take an edge, one of the endpoints must be there. That gives a branching rule. Here, what can I say? I mean, there's a way to generalize this rule which says, if you have an edge, one of the endpoints must be there in your solution in the vertex cover. If I want to generalize that rule, what do I do? What kind of thing I should say? If there is a cycle in the graph, I know that my set of vertices solution should cover all cycles. So one endpoint, at least one point of the cycle must be in my solution. I don't know which one, so I can guess and get a branching rule. But that's not good enough, right? Why? Sorry. How many? The could be a whole graph could be a Hamiltonian cycle with a lot of edges in between. So then you don't want to branch on a big cycle, because if you have an n-way branch to a depth of height k, that's like an n to the k. Here we want to get around that. Okay. So last time I suggested something. So we'll start with some. Okay, if I have a short cycle, great. Right? If I have a triangle in the graph, if I'm lucky and I find a triangle in the graph, then I know that one of the three endpoints of the triangle must be in my solution. It gives me a three-way branch, and k drops by 1 at each step. Delete that vertex, continue. But I have to be lucky and find a triangle or something short every time to have a small branching factor. So we said something last time. What did we do? There was an exercise last week. So first thing is, that's a very simple rules we do. Do some pre-processing, like here, right? Degree 3, to do some pre-processing to make degree 3 was helpful for the branching. Similarly, we'll, what are the rules? Remove vertices with degree less than or equal to 1. Then short circuit, this is the word used, degree 2 vertices. What does that mean? That if I have a vertex, then I replace this by, just get rid of that vertex x, so it becomes yz. Okay. If there is another edge yz already there, keep that as edge as well, so it will become a multi-graph. What in the whole process, what I am doing is I am maintaining the cycle structures in the graph, because I want to get an equivalent instance. So if there is, basically I want to show that if there is a k-sized feedback vertex set here, if and only if there is a k-sized feedback vertex set here, and that you can easily check that that's maintained. Right? In particular, I argue that you can't just get rid of that vertex, but you do this short circuiting. And if you have a loop on a vertex, then pick that vertex into the solution, because that is the only vertex covering that cycle. And your budget now drops by k minus 1. What that means is something like recursively look for a k minus 1 size solution there. So, at the end of all of these steps, the graph is minimum degree 3, okay, because as long as you have degree 2 vertex, you will do this, and so you have a degree, every vertex has degree at least 3. Now, there I mentioned a theorem. I wanted you to verify, prove it. And the theorem is, this is due to Erdos and Bosa, which says that if G has minimum degree 3, then there exists a cycle of length at most 2 log n. 2 log n plus 1 or something. In other words, that your branching factor is not very big. I can and can be found in it's not just there exists, you can find it. Anybody found a proof of this? This was an exercise 1 week ago.
Start with the vertex.
Hmm.
We have three-way branching.
Okay, at least 3-way branching.
So you keep on doing this. If there is an edge back to some previous vertex, you have a cycle of line 2 times the height.
So you do a BFS basically, right? Run a breadth first search. How does it go? I start at some vertex. It has minimum degree 3, I just branch, maybe more. It goes on like this, right? If I don't find any cycle at all in the so far when I am doing BFS, that means there are no cross edges, right? In a BFS, you will have a tree edge or some cross edges or edges across adjacent levels. I don't find any of them. How long can you just keep on going? What would be the height of such a tree? No. Good guess, but no. What is the height of the tree? Log n to the base 2, because every vertex has at least 2 children, right? Minimum degree is 3. That is where I am using the fact that its minimum degree is 3. So, every vertex has at least 2 children. It will be like a binary tree, except at the root I will have 3 children. After that, in the worst case, it looks like a complete binary tree. So, its height cannot be more than log n. But then at the leaf level, they all have minimum degree 3. So, where do they go, right? And if they can't proceed below. So, they all must be going up, down like this. So, you will have, so this height, in between, if you actually hit a cycle like this, then good, that's even better. You might get, this may be like this. So, this would be a short cycle. Otherwise, if I just keep going, the height would be at most log n to the base 2. And at the leaf, so here is a leaf and here is a leaf, maybe they will be adjacent because they have minimum degree 3, they have to go somewhere. So, my cycle would be, this is 1 log n, this is another log n, and this is plus 1. Okay. And if you are lucky, you might actually hit these cross edges even before. So, the cycle length is, and this is an algorithm to find such a cycle as well. Good. So, now you do not have such a big branching factor like n, but now my branching factor is like roughly 2 log n. So, this suggests an algorithm and it led me to the next exercise. So, what is the branching factor? At most 2 log n and height at most k, because so what is the algorithm now? Find a short cycle, do this pre-processing, find such a cycle using this algorithm. Now, in that cycle at least one of the vertices must be in any feedback vertex set, guess and branch. Now, the branching factor would be this and the height would be at most k. So, that would give us an algorithm whose running time is something like log n power k, right. So, branching algorithm finds, do pre-processing, find such a cycle and branch on its vertices. So, by this I mean like the vertex cover algorithm, pick this vertex, delete it, look for a feedback vertex set of size k minus 1. If you succeed, great. If not, go to the other guess, look for a feedback vertex, so recursively check for feedback vertex set of size k minus 1 and so on. So, and every step of the way you will do this pre-processing as well, that is a polynomial time, because that is what guarantees you a minimum degree 3 and hence such a short cycle. So, now the running time would be how much? So, what is the runtime? You know, 2 log n plus 1 whatever power k times again some polynomial in m and n. Okay. But this is not yet looking like an f of k, right, because there is an n there. I want an algorithm whose running time is some f of k times poly in input size. But this still has an n there, and so my second exercise last time was to show that actually this is an FPT runtime. Anybody tried? Okay. Now, I will leave it as an exercise for more people to try. What I will do is I am going to give you another FPT algorithm through a slightly different approach, which is also nice. We will do that. So, exercise, show that and see. But what is the f of k you got?
I didn't get it explicitly.
Oh.
I just got an f of k because you need to solve an equation of the form 2 to the x equals x to the c.
Okay. So, anybody else? Did you try? No. Exercise remains. Okay. Good. So, okay. Clearly, it won't be something like c power k.
It will be f of k plus n.
Yeah, that's what I've written.
Yeah.
But what is this f of k? 2 power k, 3 power k, 10 power k? No, can't be, because this log n would be larger than any constant you can put. For some, if this is some 5 power k, clearly this cannot be less than, because for if you choose n large enough so that this is more than 5, then you won't have that. So, it is some, it will be more like some k power k, okay. But check it out, see what, how you can bound this, okay. So, the idea is that you want to argue in a way that, see, there are times when this is polynomial actually. When is this polynomial? For what values of k would this be polynomial? Of course, k is a constant, it is polynomial because it is polylog, but can you can lift it more, right? What, maybe that solves your 2 power x is equal to x power say kind of thing, right. So, the up to a, for k large enough up to a point, this term will be bounded by this, and if you go k above that, this guy will dominate this, okay. That is a way to argue. So, find a k as a function of n such that if k is smaller than function of n, this will dominate it. For example, when k is constant, this will dominate it. So, up to a point, this will dominate this, and k is larger than that, you can put an f of k such that that will dominate this, okay. I have just given you everything you need to show this. But let me give you a different algorithm that is also cute. Again, we will do this pre-processing, make sure you have a minimum degree 3, and then the idea is the following. See, suppose there is a k sized feedback vertex set, right. This is my x, which size is at most k. What do we know about the induced subgraph here? It is a forest, right, because that is a definition of feedback vertex set. When you delete it, you do not have any more cycles. So, it is an acyclic graph. So, the average degree is very small here, because it is a forest, the degree of vertices here is small, which means that really, okay, this is intuition, okay, not a theorem. High degree vertices are sitting here in the feedback vertex, because the average degree here is small. So, if you have a large degree, and plus even if they are adjacent here, that can only go up to k. But if you have a vertex whose degree is like 3k, okay, then that must be in the feedback vertex is what we want to argue. I mean, that is not still true, because average degree is 2. You can have a big star here where it is a forest and still have a large degree and going up to, but roughly the intuition is that if you have too many large degrees, one of them must be in your feedback vertex, right? Because the idea of the whole branching algorithm is what, somehow if I can force one among a small set, that gives me a handle to branch, right. Because in the case of vertex cover, we said we can edge out of this 2, one is definitely forced, that gave me a handle to branch. In the case of feedback vertex set, we said one of these vertices, some small set, one of these must be in any solution, that gives me a handle to branch. So, I want to get some sort of a handle to branch here, and what the hope for the small set is that if you have a lot of high degree vertices, then one of them must be in any feedback vertex set, that gives you a handle to branch, okay. So, we will actually formally prove the following. So, this is all done. Okay, so let V equal to V1, V2 Vn in descending order of the degrees, right, where degree of Vi is greater than or equal to degree of Vi plus 1, which means basically degree of V1 is greater than or equal to degree of V2 . okay, and let, this is a notation, and here is an important claim. Yeah, so I mean after these rules are done, okay, minimum degree 3 is made sure. Like this is an interesting important claim that any feedback vertex set of size at most k must intersect V3k. So what is this saying? Yeah. So what is this saying? Take the first 3k high degree vertices, one of them must be in any solution of size at most k. Okay, and this gives you a handle to branch now. So after I prove this, do you have a branching algorithm? What kind of a branching algorithm? What kind of a running time? Hmm? Does everyone see that? So the branching algorithm would be find the top 3k high degree vertices, that's a polynomial time, you just have to count the degrees and order them, and then guess, because this claims is that at least one of them must be in my solution. Try this, delete it, try this, recurs. So you have, what is the branching factor? 3k, and the height would be at most k, that gives you a 3k power k times whatever polynomial n. So the crux of the new algorithm is going to be something like 3k power k. Good. So let's try and prove that. So before that, so this is what we want to prove, and let's prove some intermediate lemmas. So let X be a feedback vertex set. Then summation degree of V minus 1, where V is in X, is greater than or equal. Basically, they should have high degree. That's what it's going to say. E minus V plus 1. So how do we show this? So I mean, I already argued sort of the intuition. So here is my X. So it doesn't even say of size at most k or any such thing. This is V minus X. Yeah. So summation degree V in X would be all edges incident, and it counts all edges incident on this, as well as some of these edges are counted twice, but assuming even there are no such edges, then it's counting all these edges. What are the other edges left to be counted? Edges sitting inside here, right? But we know how many edges are here. So this plus cardinality of V minus cardinality of X minus 1. That's the number of edges here inside, right? Is at least I'm just counting edges. Edges, look at the vertices, edges like this, they are all counted here. Also edges inside, they are counted actually more than, they are counted twice, plus whatever number of edges inside, which can be at most this much, it may be even less because it is a forest. This must be at least the total number of edges. Sorry, is it at least or at most? At least, because some of the edges may be counted more. This may be too much more than the actual number of edges because forest may actually have fewer edges. So, this is an over counting of the number of edges. Now, from here you should be able to get that. Right, move things around. This minus x is actually contributing to degree V minus 1, and this plus 1 will come here, this V will come here. Right. Okay, but yeah. Right. Now, let us just go back to this claim. I am saying that you take the top 3k degree, high degree vertices, any feedback vertex set should contain at least one of them. If you do not even have 3k vertices, what happens? Right. If you do not even have 3k vertices, that is okay. You can still whatever number of vertices and branch. Okay, so it is not a problem. Okay, so now I want to go back to this claim. So let us see how my vertex set is. Right, proof of claim. Suppose not. What does that mean? So my vertex set is V1, V2, V3k, V3k plus 1, okay. So this lemma will be useful when I get to this claim here. All this says is sum of the degree of vertices in X is very large basically, because high degree vertices are all sitting here. Okay. So now suppose not, what does that mean? That I have a feedback vertex set that does not pick anything from the first 3k vertices. That means my feedback vertex set is actually coming from here somewhere. Now I will derive a contradiction here about to this claim. No, to the claim that you have minimum degree 3. Okay, so let us look at summation degree V minus 1, V equal to 1 to 3k. So I claim, tell me why do you believe this? You see this? So, I mean the minus 1 is not playing a big role, but this is just some term which is useful because my claim lemma is that. So, if I just add the degrees of the first 3k vertices, these are the high degree vertices, I claim that it is at least, okay, so what is suppose not means there exists an f or x and x intersection V3k equal to empty. Okay. Since I am picking k vertices from here, because the x does not intersect with the first 3k, I can sum the degrees of these k vertices, that would be less than or equal to sum the degrees of the last k vertices here, because these degrees are in decreasing order. Also they will be less than or equal to the next k vertices, also they will be less than or equal to the first k degree. So, that sum of degree of my feedback vertex set is less than or equal to, right. So, 3 times that would be, so this sum would be greater than or equal to 3 times the sum of the degree of my vertices in the feedback vertex. That is all I am saying. Agree? Because this is so far away that I can take each one, I can map it to some k vertices, and this guy will beat this, and that k will, that some degrees will beat this, the next k would beat this. So, sum of 3 times the sum of degree of b in x minus 1 would be less than or equal to this. Okay. Also, summation, okay, b I equal to, okay, degree b I greater than 3k degree b I minus 1 also I would say is greater than or equal to summation degree b in x minus 1. Why is this? Is this clear? This is again fairly obvious. So, all I am saying is you take your feedback vertex set degree, that would be less than or equal to the sum of the degree of all these vertices, because my feedback vertex set is sitting here, and this may have a lot more vertices, that is all it is saying. So, now let us add, so what is this sum? Let me add these two equations. What do I get? So, what is this sum? Sum of the vertex degree, sum of all vertices degree. So, that is like a 2 times number of edges. This minus 1 will contribute a minus v, okay, is greater than or equal to 4 times summation degree v in x minus 1. Now, I am going to use the lemma which tells you this is greater than or equal to 4 times plus 4 do some cancellation and tell me what do you get. You get 2 times E is less than or equal to 3 times V minus 4, right. But there is a contradiction, right. What is the contradiction? Minimum degree is 3. The graph has minimum degree 3. So, sum of the degrees is at least 3 times B. So, 2 times E must be greater than or equal to 3 times V. So, what have we proved? That this assumption that there is a feedback vertex set that does not intersect the first 3k vertices is false. So, there is some vertices always in any feedback vertex set of size at most k, there must be one of the vertices with the top 3k high degree vertices. Now, we are ready to branch, find the top 3k, branch, and this results in a, yeah, so results in 3k power k times some poly in n FPT algorithm. But note the contrast that for vertex cover we had a very efficient algorithm. I said the current best is 1.28 power k, but with no serious effort we could see an 1.46 power k times polynomial, whereas for feedback vertex set we still haven't seen even a 100 power k algorithm, right. The best we have seen is some k power k. It will be nice to have a constant there. And so in terms of development of a c power k algorithm for feedback vertex set, it was developed, it is there. There is a 3.8 power k is the best algorithm. It required a different technique. Okay, we will see that next week. A different technique next week, or maybe even later, called iterative compression. So just simple branching was not enough. You need that mixed with branching gave a very simple, nice, cute 5 power k algorithm, which is further improved later. Okay. So let's do one. I mean, I want to start with one more example. We'll finish it next time. So in both the examples, we've seen vertex cover and feedback vertex set. K was the solution size. Now, when I started off this parameterized complexity, I said, K can be anything, which makes sense. And we actually looked at, for example, distance from the tree, distance from a bipartite graph, that kind of things, right. So there are various ways to parameterize, and there are problems for which if you just use solution size, the FPT algorithm becomes trivial. I will give you a couple of examples. We have seen both. One is the max sat, right. Let us look at max 3 sat. Actually, we saw this FPT algorithm. What is the max 3 sat thing? You have a 3 CNF formula. And you have a parameter k. The question is there a satisfying assignment satisfying at least k clauses, right. The satisfiability question is, can you satisfy the whole formula? Okay, this is NP complete. Now, if the answer is no, I can't satisfy all entire formula. This question says, okay, what is the maximum you can satisfy? Out of all the assignments, what is the maximum number of clauses you can satisfy? So the decision version of the maximization problem is given a k, can you satisfy at least k clauses, right. So we saw a trivial FPT algorithm. What is the FPT algorithm? If I only care about some f of k, we saw a kernel. What was the kernel we saw? Yeah. So we saw a kernel. Okay, the simple kernel is we can make m to be at most 2k. Why? Because there is always an assignment that satisfies half the clauses. Okay. So if k is less than m by 2 and you ask, can you satisfy at least k clauses, and k is less than m by 2, you say, yeah, yes, there is, and you can find it easily. So if k is larger than m by 2 is when the problem becomes more interesting, at which point m is at most 2k. Okay, that's sort of a trivial kernel. And since we are dealing with 3 CNF sat, immediately n is at most 6k. Okay. Independently using crown reduction, we saw n is at most k. Okay. But let us even forget that. So now I have a trivial FPT algorithm. What is a trivial FPT algorithm? Number of variables is bounded. Try all 2 power n. Take your brute force 2 power n algorithm. That's like a 2 power 6k algorithm, and that's FPT. right? You spend a polynomial time plus 2 to the 6k. But you must be feeling somewhat uneasy about this, right? What is not so nice? See, parameterized complexity is all about, if the parameter is small, you have a feasible, nice practical algorithm, because the f of k is not too bad. If k is like 10, 20, you can deal with these kind of things. But here what we are observing is, if the parameter is small, the problem is trivial. The problem is interesting only if the parameter is large. So, when you apply your 2 power n algorithm, actually the n is large. The parameter is really, you are just exploiting the fact that k is large. So, with respect to n, so n is small, and that is all you are using. So, something, you know, not so great. We are not designing a good FPT algorithm. So, I will give you another example, which is the beaten vertex cover problem. In fact, this is what we will spend time next time. Suppose somebody tells me that the graph has a perfect matching. Okay, the standard vertex cover, and the question is, does G have vertex cover on k vertices? Right, when I say k, actually I mean at most k vertices. But you have this extra information, somebody has told you that the graph has a perfect matching. Okay. So, can you give me a trivial FPT algorithm then? A trivial kernel. Once you have a kernel, we will get. So, suppose you have a graph on 500 vertices with perfect matching, and I ask, is there a vertex cover of size at most 75? What will you say? Yes? So, it is a perfect matching, right? That means you have a matching that saturates every vertex. So, there is a large matching. How much? What is the size of the perfect matching? How many edges are there? 250 edges are there. 500 vertices, perfect matching, 250 edge. So, I have a matching with 250 vertices. How can I have a vertex cover of size at most 75? So, I look at these numbers. If you tell me it has a perfect matching, the answer is trivially no. Right? When is it trivially no? If k is less than or equal to n by 2, strictly less than, maybe equal to n by 2, it is possible, then you say no. I do not even have to look at the graph. You tell me there is a perfect matching, I just have to compare k and n, and I say, okay, if k is small, I will say no. Else, k is greater than or equal to n by 2, which means that n is at most 2k. Okay. Of course, we got this using kernel and so on, but ignore that. Now, you apply any brute force algorithm, you get an FPT algorithm, right. So, again what is happening is that if k is small, the problem is trivial. If k is large is when the problem is interesting, and we are using the fact that if k is large, your brute force algorithm itself is good enough with respect to this definition of FPT, right. So, now, so what do we do, right? I mean, there is nothing magic going on, it's an FPT algorithm and you get it, but maybe a more interesting question would be the following, right. So, see, if k is large, what is happening is my f of k allows you to spend a lot of time because k is large. So, that your brute force algorithm also gets into it nicely and you get an FPT algorithm. So, now if I suppose I change my question, in particular what is k, to be does G have a vertex cover on at most n by 2 plus k vertices? Then this is not a trivial algorithm. I mean, now everything is hard, at least more interesting, right? Because now my k is not the solution size, but it is some parameter above a guaranteed lower bound, right? So now if I ask you, I am not, so if the 75 you will say no, so now I will say what about 285? Then my parameter is not 285, my parameter is 35, the extra. So now I am limiting you how much time you are going to spend time on. This is sort of a guarantee which you can find easily in polynomial time, because it is a perfect matching I have given you. Now I am allowed a little bit more number of vertices, and your running time now should depend on exponential in that parameter. That is a more interesting question. So next time we will try and design a branching algorithm for this problem. Okay. Now the challenge is that, remember we said in a branching algorithm the k has to drop at every step for us to bound the size height of the search tree. So here it's the k is not the solution size, but k is how much more the perfect matching size, right. So now in your new instance you have to look at the matching and then see how much the matching drops, and do a careful measurement of your measure which just drops. So that makes it more interesting. Okay. And we will use our LP vertex cover LP, where we used to show that there is always a 0 half 1 solution. That will come handy, and we will start from there, and we will give an algorithm. We will get an algorithm whose running time is 4 power k, where k would be not the size of the vertex cover, where k is n by 2 vertex cover size minus n by 2. Okay. Okay. So I think we will continue on this next time. So it will be a different flavored branching algorithm, because now you have to look at the drop carefully. What, it's not the k that should drop, but this value, yes, actually k should drop, yeah, but k is not just a solution size minus the matching size should drop. So now you need to look at both these on your new instance and look at the difference, because vertex cover might drop, but if n by 2 also drops by the same fashion, then they nullify the drop. So you want vertex cover to drop heavily, but n by 2 should not drop much in your branching algorithm, branching steps. Okay, so that's for next Monday. Yeah.